Good morning, everyone. Let us start our last morning session. And the first talk today is by Xinxing Tang from BIMSA, who will talk about classical BV formalism and dispersionless integrable hierarchies. Xinxing, please.
Thanks. So good morning, everyone, and thanks for the invitation and introduction. And I will talk about the classic BV formalism and the dispersionist integrable hierarchy. And this is the plan. First, a very short introduction, and I will briefly review the classic BV formalism. And the third part is the other part of the title, and we'll talk about the dispersionist integrable hierarchy. And finally, we will talk a little about the quantum case. Okay. So it is known that the 2D topological field theory capture gravity will give rise to the integrable hierarchy. The famous example, I think, is the Gromov-Witten theory, that the Witten's conjecture, the stable intersection theory of model space on the model space of curves will give rise to the KDV hierarchy, and also there are the Boring's work on the Frobenius manifold and the integrable hierarchy theory. And here, I just want to present a connection, lateral connection between the dispersionist integrable hierarchy in 2D topological field theory and the classic geometry of Claes-Spencer gravity. It is also known as the classical BCOV theory or classic B-model theory on the Calabi-Yau manifold. More precisely, we will prove that you can see we have the integrable hierarchy, we have infinite many flows, and there are infinitely many commuting Hamiltonians, and they are given by the current observables associated to the infinite abelian symmetry of the Claes-Spencer gravity. And we will also describe a BV framework of the effective field theory that leads to the B-model interpretation. This is a rough picture that how we use the Claes-Spencer theory, use the BCOV, consider the BCOV theory on X times C star and give a B-model interpretation of the dispersionist integrable hierarchy. And the solid line is some step I will mention in this talk. So let's just do some brief review of the classical BV formalism. First, you have the free BV theory. That's a classical a free classical BV theory on a manifold will consist of the data. First, you have a complex of weak bundles on M, and here Q is the differential operator, and you will make that the section space with the differential operator being an elliptic complex. And then we have a bundle morphism from the E tensor E to the density 9 bundle. And asked this morphism is fiberwise skew symmetry and non-degenerate. And you can do the integration over M, and then you will get a symplectic pairing of degree -1. And finally, we ask that the differential operator Q is graded skew self-adjoint with respect to the symplectic pairing omega. It satisfies this identity. It also means that the omega is Q-closed. Okay, that's a field space. Now we consider the functional space. The functional space on the field space is that you can have such a definition. And we ask that each Taylor component Fk is Sk co-invariant with respect to the graded permutation. If M is compact, and we will call it a functional equivocal if each Taylor component Fk is a finite sum of the terms, that's just integration over M. And here, each di is a differential operator. Of course, if M is non-compact, we will work over the field space with compact dispose. And alternatively, you can see that the local functional space is a module tensor, the module tensor of the density 9 bundle, and here the G is the J bundle. Okay, we have the fields and we have the functionals, and we need to go on. We need the Poisson brackets, and here is the infinite dimensional setup. So we have in this case, the Poisson brackets, the Poisson kernel should be realized as the integral color of the identity map with respect to the symplectic pairing. So you can see that we have a degree 1 distribution section K0 in this space, such that this identity holds. And if we have such a kernel K0, we could define a Poisson bracket. Here is also known as the BV bracket on the space of local functionals. We will see an example to see what it is later. And of course, still that the omega is Q closed implies that Q is compatible with the BV brackets. This defines a differential graded the algebra structure on the shifted space, functional space. And of course, you can extend the bracket to be on a larger space, or we know as the observable space. It's the functions on the fields. You will have the bracket. We will also see such an example later. Okay, now we have a free theory. To describe the dynamics of a BV theory in general, we have to consider an interaction term. And we have already, there is a DGLA here, so we have the Murray-Gardon equation and can solve it, and you have describe some deformation. So the explicit definition is as follows. You have a local functional I of degree 0, and it's said to satisfy the classical math equation if this equation holds, this identity holds. We have the differential operator induced on the functional space, and we also have the BV bracket on the local functional space. Okay, it follows that if the solution I, if we have a solution I, then it induces a new differential. It's given by Q plus I, the bracket with respect to I, and you can denote it by Q plus delta I. Here, the action functional with local function I is given by the first part is the free part, then you have interaction part. Okay, let's just look at a very simple example, and we want to describe the tensor theory in the BV formalism or in the BV setup. First, you have a 3-dimensional oriented manifold, and of course, G is the lead algebra with a non-degenerate trace pairing. And now, in this case, the space of fields, E, is just the differential form space tensor G, and also for some reason we shift by 1, the degree by 1. And then we also have the -1 shifted symplectic pairing, just given by you take alpha, wedge, beta, and take the trace, and then finally do the integration. And also in this case, the differential Q is just the drum differential. And we can write down the tensor action functional as follows. And you can see that the first part actually is the free part, and the second part is the interaction part. Okay, we can consider the variation with respect to the fields. So you can see that using integration by part, you have the delta Cs, you finally can get a formula as follows, which implies that you have a infinitesimal action on the fields is given by this, just this part. And also, since since the field space is the deformed space tensor G, and actually we can decompose it in the deformation according to the deformed degree, and you can see that now you have A is 0 form, 1 form, 2 form, 3 form. And you can also rewrite these identities, and you will get, for example, I just write the first two identity that's the infinitesimal action on the 0 form is just given by this one, and the infinitesimal action on the second term and the 1 form is just given by this one. And if you are known with the Chevening-Edinburgh complex and of the algebra, or you can see that this delta Cs is just the Chevening-Edinburgh differential on the field space. And then it induces a differential on the functional space, and you can check that this is indeed a differential operator, and it is also equivalent to see that the BV bracket between the tensor action functional is 0. Okay, now we can also see some observables in this case. In the beginning, we talk about the no-go function with integration over M, but we can also talk about some point observable or one circle observable, two circle observables. That's if you give me a point x in M, and you can also give me a vector in the dual algebras, and you can define a linear observables OXV of degree 1. It just take A and we pick up the degree 0 part of A and consider the natural pairing. And in general, you can have the chain map showing this complex to the observable complex with such a differential delta space. This is a point case. Just pick up the zero degree part. And of course, you can consider the degree 1 part. That means that now we choose a cycle S1 inside M, and also we choose a representation R of G, and then we can define a linear observables. Still from the fields, still a function on the fields, and here you pick up a field A and you choose the one form part and take a trace on the representation side and finally integrate over S1. And of course, we can do some computation that this is a local, say this is a local functional and this is observable. And you can have these BV brackets just given by the delta space on the fields and expanding it, and finally it's zero. You see that here we define the linear observable associated to S1 and R is delta space closed. Of course, you can consider two form and pick up two-dimensional cycle in M and continue. Okay, since in the beginning we talked about that in the BV theory we have a complex of vector bundles. We have a second space, so we can consider its Q-cohomology. And we also ask that it's elliptic complex, so we get a finite dimensional graded vector space H here. And we can also, do the same thing as before, and you have the space of form functionals on the cohomology spaces, and you have OH. And Q and omega is compatible, so your symplectic pairing descends to a symplectic pairing omega H on the finite dimensional space. And in this case, you can, since it's finite dimensional, you can just take the inverse to define the BV curl on the cohomology, and it also induces a pairing on the functional space. Okay, since we have, in the beginning, we have a big fields, epsilon and its functional space, now we have, it's just the cohomology part. And we also talk about the action functional, we talk about the local functional or local solution of the classical master equation. So we need to ask ourselves, from the solution I of the classical master equation, how to get maybe a solution in the classical master equation in this setup. We need to do some homotopy transform. So to do that, we need the contraction data. We can regard our cohomology space H just as a complex with zero differential. And the contraction data is the I pi p hat. You can see this graph. And it means that here we have two co-chain maps, I from H to epsilon and pi from E to H. Here you can just understand it as the basic embedding and projection. And you also have a linear map p hat from E to E, such that your identity map in H and identity map in E has a decomposition in this way. And of course, sometimes we will also require that the p hat satisfies these relations. Oh, this is the contraction data. And usually a contraction data can be constructed by the Hodge theory and the heat kernel. Suppose we have a linear operator QGF also from E to E, and such that the sum of the composition with Q and QGF is a generalized Laplacian. Then we can consider the corresponding harmonic spaces H. That's QF equals to 0 and QGFF equals to 0. And the standard Hodge theory implies that we have the isomorphism that the cohomology space H is isomorphic to the harmonic space. Now, since we have the heat operator and we can consider its integral kernel, then we will obtain the contraction data using this isomorphism. In this case, I is just a harmonic embedding and pi is a harmonic projection. And you also have a representation. You have a form of the p hat. And also it has an integral kernel, can write it as p. Here, HT is the heat kernel operator. Here, the P is actually the propagator in the BV theory that we will use later. Okay, with the help of the construction data, what we can do next? It follows that from the construction that we can use some tree formula to define a formal function on E. That's here that you have this formula. Here, the functional W gamma IP is the Feynman graph integral with the vertex being assigned by I and the internal H is the propagator. We put it P and you have some extra H being the input of your functions. And here the summation is over all the possible connected trees. And furthermore, we can define the homotopy transform IH of the local functional I being just use the tree formula first and then restrict to H. The standard proposition or the standard homotopy transfer theorem tells us that if you have a solution of the classical master equation and you have a contracting data and its homotopy transform IH satisfy the following classical master equation on H, since the differential on H is 0, so you have such an equation. Of course, we can generalize the homotopy transform method to the situation that you have a classic BV theory on the product manifold x times y, and you perform the homotopy transfer just along x. It also means that you do the compactification on x. And similarly, you can define the contraction data partially or relative to such a standard projection. And then you will see that you have the classical mass equation and this theory. And when you do this compactification, you will get a theory. It means that we just integrate out the massive modes along x here just at the classical level, and then we will obtain here the right-hand side will obtain an effective theory on y. Okay, this is I just want to review some basic things about the BV formalism and some basic construction and basic idea. And now we can go to the other part, is about the dispersionless integrable hierarchy. And we will see how it is related to the classical master equation. Okay, still some basic setup. Let H be a finite dimensional graded vector space, which is known as the small phase space of 2D topological field theory. Here, H could be our cohomology space, or H could be other. In other model, it's also some cohomology space. And H tensor CT, we called it the big phase space. Here, T is just a formal variable. Well, if we want to capture gravity, and here T just represents the gravitational descendant, and you will have infinite many flows along the tube direction. And in 2D topological field theory, you have the famous genus zero correlation functions. It's a graded symmetric functions on the big phase space. And in the following, for simplicity, I will assume that H is purely even. Okay, continue the definition. And we can choose the basis of H, of the small phase space. Here there is a special one inside that is P, we denoted by P, just a one, we call it is the identity element in H actually. And of course, when you times the t case power, finally you will get a form basis of the big phase space. And if we consider the 3-point functions with the primary insertion and also p's inside, then you will get actually a constant G alpha beta. It will give you a non-degenerate product on the small phase space H. And for the basis you choose in the big phase space, and you can choose the corresponding coordinate, linear coordinate, and you have the genus 0 correlation function. You can do some generation functions on HT, and you can define in this way, and just have some insertion here, exponential insertion here. Okay, and the famous and I say the most important identity in the genus 0 theory should be the genus 0 topological recursion relation. And you can see that the recursion that you have the I plus 1, and the right hand side is just I and others. And if you use these formulas, and you will find that all the 3-point functions that if you just have the you have the descendant insertion, finally it can be reprinted by the functions with just primary insertion. And also use this topological recursion relation diagram, and we can develop some constitute equations, and which give rise to the dispersionless integrable hierarchy. Okay, now let's see what is the dispersionless integrable hierarchy. And we can promote the bk alpha to be a function of bk alpha z, depending on variable z. Here we consider the local functionals of the form. And you can introduce Poisson brackets in a standard way that here we have the delta k0, delta L0 means that the Poisson bracket is non-trivial only on the primary state. Of course, in a standard way, it induces a Lie bracket and space of local functionals. Okay, then we consider what is the possible Hamiltonian or Hamiltonian density in this setup. Let gk alpha be the restriction of the 1-point function. This is 1-point function we defined, and we restrict it to the small phase space. You get this one, and the proposition is that the corresponding Hamiltonians, the corresponding local functionals are Hamiltonians, and they commute with each other. You have many different ways to prove these propositions, and yes, just as I said, we can use this to use the constitutive equation to describe the dispersionless integrable hierarchy, and find that equation first, and of course the compatibility tells you that they commute with each other. And also, De Bruijn has some theory on the Frobenius manifold, tells you that these commute with each other. And such infinitely many commuting Hamiltonians will generate the dispersionless integrable hierarchy. And here we want to use the BV formalism, and I want to use some other idea to explain or derive this proposition. We have 3 steps. First, we can construct DGLA. We can enlarge the bosonic fields bk alpha z by introducing additional fermions. And we can also enlarge the space of local functionals. Now you can see that we have the bk alpha, we have also eta k alpha and its derivatives. Of course, and the bracket on the local functionals is also induced by the Poisson bracket just on B0 alpha. And you also have a differential on the functional spaces, and it's induced by it on fields, defining a differential on the fields in this way. And you can prove that the triple, the space of functionals, the bracket, and the differential forms the differential Z2 graded Lie algebra. Since you have DGLA, so you have the Morey-Gardin equation, and you can construct the solution to describe its deformation or some interaction. Here, we can define the following functional I. Here, this is the one-point function, just 1 point without restrict to the small phase space, and you have eta k alpha, you have a formula inside, and take a sum. And we can prove that such action and such a local functional satisfies the following Morgan equation with respect to the DGLA. And in fact, when we prove it, we found that this equation is equivalent to the genus zero topological recursion relation. Okay, then we can consider the restriction. Since we define the differential induced by the differential on the fields, and we can choose maybe just the kernel of the zero, and you can see that the stationary states is given by the bk, the descendant part, corresponding part is zero, and the eta you introduce the former part is the constant fields. Then you can let IS denote the restriction of I to this sector. Now in this sector we have the delta x to 0. Then the Morgan equation implies this one. And furthermore, you can expand this equation and you will get such a brackets relation with some coefficient in the beginning and it's 0. It also says that these two local functionals commute with each other. And then we give the proof. Okay, as I explained in the beginning, we want to explain how the dispersionless integrable hierarchy structure arises from the classical B-model theory. Basically, it is motivated by studying the projection. You have projecting pi from x times sigma to sigma. Here, the sigma is a surface with a Calabi-Yau structure, so it should be C or C star or just elliptic curve, E tau. And since we studied the B model with the BCOV theory, we also need that X is a Calabi-Yau manifold. We can put the B model on the product manifolds and then compactify a non-X. Then we obtain an effective 2D K field theory on the Riemann surfaces, here the sigma, that encodes the geometric invariance of X. And we find that the induced B-Riemann equation of such effective theory encodes precisely the integrable hierarchy structure associated with target X. So let's see the picture again. This is something we just described, the dispersionless integrable hierarchy. And yes, the genus zero topological recursion relation tells you that we construct another local functional satisfy the Morgan equations. And from this side, we want some BCOV theory on the product manifolds and do a compactification and get some H-valued BCOV theory on C star. I will talk it later. And since this is C star, and here we construct everything just do the cycle integral, so we need to do some topological descendant. And you will get the Morgan equation associated with the current observables. And finally, you can see these two. Not really. These two just identify with each other. Okay, maybe let's see what is the H-valued BCOV theory. The H-valued BCOV theory on the Calabi-Yau manifold Y is that we have the fields is given by the polyvector fields on Y and the tensor H. And of course, here we introduce a descendant variable T. And since Y is Calabi-Yau, so there is a holomorphic volume form on Y. And the differential now is given by partial bar plus T partial. Partial bar is just the anti-holomorphic derivatives, and here the partial is the divergence operator with respect to the holomorphic volume form. And also, you have the holomorphic volume form. You can define a trace map on the polyvector field part. And just say use your polyvector field to contraction with your holomorphic volume form and y omega y and do integration. And in this theory, you can see that there is a BV kernel that is of this form. and here. With respect to the pairing given by this trace, here the partial times 1 delta y is the integral kernel of the operator partial, of actually the BV operator. And we can see that the triple, you have the fields, and you have the differential operator Q, and you also have some BV kernel or the Poisson kernel. Here you define the BV data. And by the standard BV formalism, you can see that now the differential operator induces a differential on the local functional. And the BV kernel define the BV bracket also on the local functional space. And you can also enlarge this definition to from the local functional space times other functional space to other functional space. Okay, then we can define the classic BCOV interaction IYH using a trace map, and with the help to the genus 0 topological recursion, topological functions here. And we can see that we define such a BCOV interaction is the solution of the corresponding classical master equation. Okay, so now we want to see the case y equals to C star. And in this case, you can write down the fields of the H-varied BCOV theory on C star is just, this is a polyvector field part, this is 0 part, and here there is polyvector, there is a 1 polyvector here, and this is a field. And with such a decomposition, you can represent an actual field in components here. And here there is a partial z. And giving L in this space, we can also define a form-valued functionals on the field space here. And you can also introduce a differential delta just as follows with how we do it with the bk and eta k. And then the differential tells you that if you compute the differential, it will be this, you will get this one. Again, since it's a form-valued functional, so you have one form, two form, decompose it, and you can rewrite it component-wise, and you will get this and this. Now if we fix the cycle, say representing S1 inside the C star, you will have two observables, and this is the local observables in the BV formalism. And this is another one to the cycle integrals, some Hamiltonian type integrals, so you have we call these current observables. And you can see the relation between their density is this. Okay, again, if we just consider the space of the cycle integral form here, and also you can define a differential induced by it on the density, and you have also a bracket induced by the BV bracket given by the local functional on C star integral over C star. And you can see that you get another triple from the DGLA, Z2 graded. And you can also, in this setup, you can consider the following power series. Almost is some kind of one-point functions. And then the BCOV interaction is given by it's the corresponding two-form part and do some integration over C star, which will solve the classical master equation. And if you consider some descendant on the topological side, you have the cycle integral part, the current observables, you will see that this is satisfy the Morigata equation with respect to the DGLA you obtain. This one. Okay, it's natural to say that we can identify the construction here on the lambda k alpha, rho k alpha with the fields in the dispersionless integrable hierarchy bk alpha and eta k alpha. And under this identification, actually the two DGLS coincide with each other. And this is the dispersionless integrable set, and this is the BCOV set. But in the BCOV side, since you use the BV formalism, you have more observables, you have more functionals. Okay, let's see how apply it to the B model set. As we said in the beginning, that you have now X and Y are two Calabi-Yau manifolds, and we can consider the BCOV theory on X times Y, and then do the compactification along the X directions. You know that the BCOV fields on the X times Y are just given by the polyvector field on the product manifold with descendants. And if we choose a countermetric on X, and yes, we can still have some dual operator, and you have some Laplace operator to hot theory, to the heat kernel theory. You can see that the hot theory tell you that in this case, the fields with the differential operator with descendants is isomorphic to the harmonic space, here also with some descendants. And as I said before, you can construct some contraction data relative to the projection. And then you have this, first you have the classical master equation in this part, and when you do the compactification, you will get HX valued theory on the manifold Y, and you get some, to do some kind of compactification, we'll get something here. And if we choose Y to be C or C star or the equilibrium curve, and you can take the dispersionist image of the solution of the classical master equation in this part, and this dispersionist image will define the interaction of our HX valued BCOV theory on Y. And this also gives the dispersionist integrable hierarchy for the B model on X. So it's our picture. Finally, I want to talk a little about the quantum case. And in the classical case, we just use the tree formula to define the action function or to define something else, but we can also concept other graph, the hygienius graph, to do some to define the quantum mass equation, to define the quantum theory, to do some corrections. And here we can consider the quantum BV master equation. As I explained, you can use all the graph formulas, and not just tree. And but there are some problems about the convergence, and you need to be very careful about it. And the corresponding, but we can deal with it just as we would do here. That you can do the corresponding effective BV quantization, but translated to the vertex algebra constructions. And in this case, you can say that your Lie bracket in the beginning, you leave to the operator product expansion. That your fields, the primary fields here, you actually satisfy the OPE. The singular part is given by this one. And the classical action functional, now we write it as I0, should get some quantum corrections to become a action functional with density. You have some hygienius part and satisfies the equation. The other actually some more other Morrigan equations. Here the bracket is the communicator of the Kerr vertex operators, but we ask this involves all multiple contractions, not just the tree case. Simple example, if we write I, just do some genius expansions, then the genius one part of this equation will tell you that you will get this equation by some degree reason. And here you have two brackets. The first bracket with respect to 0 is just the original bracket induced by the Poisson bracket on the fields. And the second, you consider the one graph, consider the genus one graph, then you will get bottom brackets in this way. And of course, you can do other high genus expansion to get more complicated the bottom bracket.
So it's no more dispersionless.
What is dispersionless?
This one, just one.
For simplicity, I just want to talk about that maybe x is the points and sigma is the e tau. And when you do the complexification, and actually x is points, so the cohomology is just one dimensional. It corresponds to actual KdV case. And we have the fields bkz and eta kz. K is bigger than 0. And in this case, we can say we still have the dynamic fields. It's just the primary B0z is given by the derivative of the free boson. And the others are the background fields. They have commutative OP. They don't have the single parts, the OP. So, and we organize all the other fields in this true one with the true one. And one can prove that there exists a unique J belongs to this space, and with the leading term is given by the J0 is this. You can say that the J0 is just corresponds. You can check that the J0 corresponds to a classical level, and there is no Z derivatives in the formula in G0. And such that finally, if you define I in this way, and such a local functional satisfies the Morgan equation that we want here. Okay, we can do the same thing, and we can restrict this I to a stationary sector as before, and then in this case, the quantum mass equation will become this one. And you expanding the coefficient eta case, and this is equivalent to such a commutative relations between these two fields, between these two local functionals. And if you take the classical limits of this one, you will give rise to the dispersionless KdV hierarchy, since we consider the case x is just a point. So yes, and also with such Hamiltonians, you can construct the character. Actually, the character here is the generating function of stationary sector of quantum BCOV theory on in the bigger curve. You can construct a character in this way. Here, the H is the Heisenberg vertex algebra with respect to the B0, and L0 is the conformal weight vector. And you can see that this character coincides with the generating function of the Gromov-Witten theory of the elliptic curve under the mirror symmetry under the Boson-Fermi correspondence. The computation is given by Okenkopf and Pandam. And here, I just show a very simple example that's x is a point. Of course, you can consider other complete case. And key point here that since we consider the BCOV theory, we do some integration over E tau over other Riemann surfaces, and we want to from the Lagrangian setup to the Hamiltonian setup, we need to from the surface integral change the surface integral to the cycle integral. So we also do some work on this when you. Okay, sorry, what happened? Okay. So when you want to do such transformation from the Lagrangian side to the Hamiltonian side, you need sometimes you need to introduce some contact term, and sometimes you need to do some descendant operations in the topological side. And maybe that's what I want to see. Thanks.
Thank you, Xinxing. Any questions or comments?
Thank you for your talk. I have, so you mentioned this topological recursion relations, and I have two questions. Maybe I don't know might be not your field, nevertheless. One is that, of course, we can so these relations can be written for not necessarily dispersionless case, right? So it can be written also for the full hierarchy.
Yes, for case, yes.
So do you observe something like this here?
And we can also do some expansion here.
Yeah, that's
yes, we can get some relation when we consider that is constructed with respect to the topological field theory, but we see that they are different. We see actually here I don't talk too much. Here when I get from here from the compactification you get classical mass equation, get the solution of classical mass equation on the right hand side. If you want to, actually here I still have some partial z in the x in y direction. We need to take the dispersionless limiter again, and then we will arrive the really dispersionless integrable hierarchy. Yes.
And second is about what is called abstract topological recursion by Kontsevich and Soibelman. Maybe it is also can be formulated in your terms.
Okay. I see.
It's just a suggestion. It's not probably a question.
Yes, there are many topological recursion relations in the topological field theory, and yes, thanks.
More questions or comments?
I have a question.
Yes.
Thank you for your wonderful talk.
Thank you.
My question regarding the KDV hierarchy.
Yes.
Here you showed you got a KDV hierarchy through some operator W or with the integral, right?
Yeah, W infinity algebra.
Okay.
Yes.
So that bracket is a regular bracket or Lie bracket?
Lie bracket.
Okay. So the hierarchy you got here is same as the integrable KDV hierarchy through recursion operator, which means you have two Hamiltonian operators.
Yes.
J equals D, K equals D squared, DQ plus 1 over dm plus is completely the same.
I don't think it's the same. We don't consider the second person bracket here.
Okay.
We don't consider it.
So you don't have since the hierarchy in the KDV chain. So the first equation, typical equation, is the third order. Second would be fifth order, and so on.
Yes, I understand that.
It's same as.
No. Actually, here it's not really the KDV. Should be not the how to say the KDV Hamiltonians. It's not. Actually, it's not. Since we consider the torus case, which kind of point times torus. So actually, it's here we have some torus. We use here. You will use the no matter a propagator or something else. We just use the elliptic curve and elliptic functions to do the computation, and that's something different. It's not maybe some kind of quantum type since we have tau here. If we want to write everything quite clear, there's some tau information here. Yes.
Okay, thank you.
It's not quite the same. Yes.
Okay, not the same. Okay, thank you.
Any more questions? Comments? So let us thank Xinxing again.
Thanks.